Good morning, afternoon, evening, time of day that you are choosing to watch this video. Welcome back to another week. Thanks for getting through your exam, and I didn't get any emails that were freaking out about any sort of tech issues, so that's good. So as far as I know, everything should have gone smooth sailing. Do remember that the grade that you initially see in the grade book is not the final grade for the exam. I still have to go through and grade the short answer questions and your calculation and all that stuff by hand. So keep an eye out for that, and I'll let you know when those get all finished. All right. So whilst all of this is going on, we still got to keep on trucking through our material, right? So we're going to go ahead and do that. So for today, we're going to talk about salinity and salt in the oceans, as well as some other impacts of gases in the ocean and things of that nature. And perhaps we'll get to talking about the atmosphere as well. We shall see how long these videos take, okay? So salinity. The best thing to do initially is to remind ourselves what salinity is, right? What does it mean to be salty? And so maybe take a moment, pause the video if possible, and recall what salinity is and what the average value of salinity is around the oceans. Take a second, and then if you recall that the average salinity is actually only about 3.5%. So salinity itself is the ratio of the amount of dissolved salt in the amount of water. So salt adds a whole different aspect to our oceans. We talked about just water in general and the really unique properties of water, and what makes our planet just so stinking cool and unique is all of those things. And now we're going to add salt into the mix. So if we were to consider, the saltiness of our oceans and to take an average of the saltiness around, and we were to consider the Atlantic Ocean in particular, this is what we would observe. So on our bottom x-axis is salinity values in parts per thousand. Remember that parts per thousand is very similar to percent. It's just the decimal is moved over to the right one. So like our average salinity is 3.5%, which is the same thing as 35 parts per thousand. And then temperature, air temperature, is indicated here on the top. Water temperature, excuse me. And then our latitude is on our y-axis. So the North Pole is here on the top, South Pole is here at the bottom, and the equator is in the middle. So some things to point out here is the fact that the salinity values are not even everywhere, right? There's this little itty bitty dip. If you were to flip this slide over, flip your phone or laptop over, whatever you're watching this on, it would look like an M, right? Like the letter M, like Mallory, M. So we can see there are regions where the water is less salty, and regions where water is more salty, and then another dip here at the equator as well. So the pattern that we see for salinity through the Atlantic Ocean in particular does not follow the same pattern as temperature here. So some things to consider around that would be, what modifies salinity? So how can you add salt to water, or how can you make water more fresh? So maybe pause the video here for a sec and consider how you would add fresh water back into the system. So how would you add fresh water in a natural earth science process? How would you add water to a system? By precipitation, right? And then how would you take away water or leave salt behind? It's called evaporation. So if we were to consider a graph of, I got two graphs here. One on the left is looking at once again, latitude is on our x-axis here, and precipitation is on our y-axis, and I think we actually have the image here is a little bit cut off, but there's two y-axes. So the blue line is evaporation and the red line is precipitation. So consider pausing the video again and looking at the pattern that you see. What do you see, right? Are things flat? Is there some sort of, are there peaks? Are there valleys anywhere? And consider those ideas, and where do those variations happen in regards to where we're located on the planet, right? So for example, here we can see near the equator, we have a massive peak in precipitation. There's a big reason for that, actually. It's called the intercontinental, or the ITCZ, the Intertropical Convergence Zone. There we go. So we have a lot of precipitation near the equator. We also tend to observe a pretty decent amount of precipitation near like the middle latitudes area. So just north of where we are, say for example, like Seattle, we always talk about how Seattle is super rainy. Whereas there's regions of high evaporation in other areas, right? So think of the world's deserts. If you were to look at a picture of a globe and where you would see the world's deserts, like the Southwest U.S., so like Arizona, New Mexico, even southwestern California, that's a whole desert there, or the Sahara Desert in Africa, the entire Middle East, right? Those are all very, very dry regions in the Northern Hemisphere. In the Southern Hemisphere, we actually have Australia. There's not a whole lot of land in the Southern Hemisphere, so it's kind of harder to see those correlations, but Australia is just one big old desert. With in the northern part, it's a bit more tropical, but for all intents and purposes, Australia is a big old desert. So just, thinking critically and seeing where we observe, our world's rainforests and our world's deserts, and considering, where on average the greater precipitation or evaporation occurs. So when we subtract the precipitation from the evaporation, we see this pattern here, which is the blue line on the right-hand side. The latitude is still on the x-axis. Salinity is on the right y-axis, and evaporation minus precipitation is on the left y-axis here. And we can see that these two patterns fit a heck of a lot better than what we see over here on the left-hand side. So once we kind of take into account both evaporation and precipitation, then the pattern fits better. And again, this is slicing through the Atlantic Ocean. If we were to look at other oceans, we would see something similar, perhaps just not as concentrated because, the Pacific Ocean is freaking huge. Much larger than the Atlantic Ocean, but we'd still see something similar, right? So these areas of higher evaporation or higher precipitation, near the equator would see kind of localized lower salinity rates, whereas regions of higher evaporation, we see higher salinities, right? So it's this a pretty common conclusion to come to. And if we were to think of the components of salt, like what makes up salt, right? What are the atoms that make up salt? Perhaps you've heard about it this way, and think of just table salt, right? Or kosher salt. It's NaCl, right? Sodium chloride. But if we consider the other ions and molecules that are in seawater, it turns out that there's actually a pretty interesting distribution of different types of molecules. So we call these the constituents of salt. So what makes up the salt? So I like this image a lot because I think it really nicely shows, once again, that idea of 35 parts per thousand in terms of salinity value and the average salinity, right? So if we were to have 965 grams of pure water, and then about 35 grams of salt, put those two things together, add those together, it makes 1,000. So the salt portion consists of chloride and sodium, and then a bunch of other molecules as well. So the idea here is that it's not just salt. There are other features in here also. And we can break these things down a little bit further. I have another visual for us, right? So we can break these down into major constituents and minor constituents and then just straight constituents. So the biggest take-home point here, my friends, is that chloride is really the breadwinner here. It takes up most of the percentage of the major constituents. And then sodium comes in a not so far second at 31%-ish. And then we have sulfate, magnesium, calcium, potassium, and then other. So then this little sliver of pie can be blown up into its own pie. So some things to look at here would be of our minor constituents that carbon dioxide as a gaseous state is the greater constituent, or the greater constituent of the other. And then there's bromine and carbon and nitrogen as a gas and oxygen as a gas. And then another slice of other pie, which can then further be broken down into other trace constituents. So questions that you will probably encounter would be, what is the greatest major constituent, or what is the second greatest major constituent of salt in seawater? So this is where you would get that information. So where do all of these things come from? What are their sources? You always got to look for sources, right? Sources are a big thing of really just everything. And so this schematic, I think, does a really nice job of showing all this stuff, right? So, where does sulfur come from? Well, we have volcanoes that erupt and then spew out sulfur into the atmosphere. And then we can also, there's other reactions within the atmosphere, and we can pick up chloride and sulfate, as well as CO2 and methane and things of that nature. And then in our river discharge, we can have various types of ions like bicarbonate, calcium, sulfate, and sodium, and biological processes that can bring all of these gases and these molecules from the surface of the ocean to the depths. Things can also be absorbed and precipitated. There's also dissolution from the rocks and sediments at the bottom of the ocean kind of mixing up into the water and breaking down. And then, of course, calcium and potassium and magnesium sulfate from our ridge systems, right? Think of when we talked about sediment and what makes up sediment. Calcium is part of that. Silicon is part of that, right? And then this is really just all one big circle of movement of different molecules and ions. And then considering variations in salinity. So kind of already talked a bit about this when we looked at, how just a few slides ago, look how the surface salinity varies from place to place. So things to consider: ways that decrease salinity. So you're adding fresh water into the system. Precipitation we already talked about. Runoff is a whole nother thing as well. Sea ice and icebergs melting. So if we're adding, fresh water into the system, then we're decreasing the salinity at the surface, right? And then ways to increase salinity would be sea ice formation. So the opposite, right? So when sea ice forms, it leaves salt behind. It's like, bye salt. It was great hanging out with you for a little while, but time for me to go solid. And so that can leave the salt behind. This is actually a huge driving force in what we call the thermohaline circulation. We got really cold, really salty water that can then sink to the depths because it has a higher density. And then, of course, evaporation as well. So really, overall, the big take-home message here is that water, geology, and biological processes are all connected through salt and mineral exchange. So it's like all this stuff all put together. So the next video, we're going to consider the gases of the oceans as well as the atmosphere, and going into the carbon pump and biological pump. So stay tuned.